Awesome choice! Let's dive into some introductory data and analysis together, also known as statistics. Here's our timeline moving through this discussion. We're going to start with statistical test overview, and then talk about what significance and p-values mean, and then we're going to end with going over two specific tests that you're expected to know about for Life 102 biology, okay? So let's go ahead and get started with statistical tests overview. To do this, let's revisit our previous example looking at the fin length in bluefish versus orangefish. As you can see in our data table, the average fin length for bluefish is 4.33 centimeters, right? And the average fin length for orangefish is about 4 centimeters. So, at a glance, it looks like the bluefish have longer fins than orangefish. But, can we be sure? How can we know whether these results are significantly different enough to actually mean anything? How can we know for sure? How can we be sure that these results did not occur just by random chance, or at totally random, right? We can answer these questions by running statistical tests. Now, when people talk about data analyses and statistical tests, we hear two phrases getting thrown around all the time. Those phrases are statistically significant and p-value. So before going too much further, let's just break down what these two terms mean. As you may recall, nothing is ever proven in science. For something to be proven true, that would mean that we would have to test all individuals over an infinite amount of time, which is just not possible. So, what we do instead is design experiments to either support or refute hypotheses. But even a perfectly designed experiment will still be impacted by random chance. How can you know that your results are actually due to the differences in the independent variable and not just due to random chance? By running statistical tests. This is where our terms statistically significant and p-value come into play. Statistical tests help determine whether our results are due to random chance or if our results are due to a relationship between the variables, independent and dependent, variables that we are studying. We say our results are statistically significant if the test we run determines that our results are most likely due to a relationship between the variables we are studying, meaning our results are not due to just random chance. Looking back at our fish example, if we ran a statistical test and the test determines that our results are statistically significant, that would mean that our results, the 4.33 centimeters versus 4 centimeters, are significantly different from one another to actually mean something. Meaning, we can expect that in the real world, bluefish probably tend to actually have longer fins than orangefish. It also means that we can be confident that our results did not occur by just random chance, but that our data likely reflects what we would see in the real world, beyond just our observed sample. But how can we tell whether or not something is statistically significant? We can determine whether something is statistically significant by running a statistical test, which outputs something called a p-value. I will show you the steps on how we run a statistical test later, but for right now, all you need to know is that the p in p-value stands for probability, because the p-value represents the probability that the results we saw were due to just random chance. Since it's a probability though, that means that a p-value must always be between 0 and 1. So a p-value of 0 would mean that there is a 0% chance that our results were just due to random chance, meaning our results were not due to random chance. In this instance, we would say that our results were statistically significant. In contrast, a p-value of 1 would mean that there is a 100% chance that our results were just due to random chance, meaning that our results were definitely due to random chance, so we cannot really trust our results, and these results we would definitely say are not statistically significant. Make sense? So looking back at our example, let's say that we ran a statistical test on our data from before to compare the averages between our two groups. Actually, before diving into our example, one last thing about p-values that is very important is that p-values are directly linked to hypotheses. This is really important, so be sure to focus up. Remember, nothing is ever proven in science, right? Instead, we simply support or refute hypotheses. We remember that? Yes? Well, this is how we do that. This is how we either support or refute a hypothesis. This is how we determine if a hypothesis is supported or refuted. with our p-value. Specifically, p-values are directly related to our null hypotheses. If we have a very low p-value, like between 0 and 0.05, like super low, then we would reject our null hypothesis. Our null hypothesis would be refuted, meaning our alternative hypothesis would be supported. In contrast, if we have a higher p-value, like between 0.051 and 1, then we would fail to reject our null hypothesis, meaning our null hypothesis is supported. So now, let's look at this example in the context of our example with different colored fish. So looking back at our example, let's say our alternative hypothesis is blue fish have longer fins than orange fish. And our null hypothesis is there is no difference in fin length between blue fish and orange fish. Okay, now let's pretend that we ran a statistical test on our data to compare the averages between our two groups. And our statistical test output a value of 0.27. This would mean that there is a 27% chance that our results were due to random chance. In science, we consider that a bit too high to be considered statistically significant. A good rule of thumb is that we never really want there to be a higher than 5% chance that our results are due to random chance. If our results have a p-value of greater than 0.05, that means our results are not statistically significant because there is a higher than 5% chance that the results we got could have just been due to random chance. Now, let's evaluate what a p-value of 0.27 actually means in the context of our example. Because our p-value is greater than 0.05, we fail to reject the null hypothesis, meaning the null hypothesis is supported. There is likely no difference in fin length between blue fish and orange fish. A p-value of 0.27 in this context would also mean that the difference seen in average fin length between blue fish and orange fish is not statistically significant. This means that even though our samples show that blue fish have longer fins than orange fish, there is a 27% chance that the difference found in average fin length between blue fish and orange fish was seen by chance, and not because blue fish actually tend to have longer fins than orange fish in the real world. Alright, and with that, let's move on to your next check-in question. This is check-in number 10. So looking for question number 10. Jamie is conducting an experiment to help answer the research question, does age impact weight loss? Jamie's hypotheses are as follows. Their alternative hypothesis is younger people lose more weight than older people. Their null hypothesis is that there is no relationship between age and weight loss. To test their hypotheses, Jamie gathers a sample size of 100 voluntary participants. 50 of these individuals are 15 years old. These are group 1 individuals. 50 participants are 70 years old. These are group 2 participants. And the average weight loss in group 1 was noted to be 6 kilograms in 1 month, whereas the average weight loss in group 2 was noted to be 2 kilograms in 1 month. Jamie ran a statistical test on their data that produced a p-value of 0.042. From this information, determine the following. Is the difference in average weight loss between group 1 and group 2 statistically significant? What is the percent chance that Jamie's results were just due to random chance? Should Jamie reject or fail to reject their null hypothesis? And then finally, what does this actually mean? Okay, so now just keeping track of where we are, we've now gone over just a brief overview of what statistical tests are, as well as what is meant by statistical significance and how to interpret p-values. So now let's go ahead and go over 2 common types of statistical tests, our t-tests and chi-squared tests. Now, there are many different kinds of statistical tests out there, but these are the 2 that we will be using in this course. And these are 2 of the most common ones, hence why they're used in this course. Sound good? So let's start with diving in to when we would use each one of these tests. A t-test is used to compare the averages of 2 groups together to see if the difference between the 2 averages is statistically significant. A great example of this could be Jamie's experiment from checking question 10. Now, Jamie's experimental design is not perfect, but this is a good example of when we would want to use a t-test. Here, Jamie is looking at 2 groups, 15-year-olds and 70-year-olds, and comparing the averages of the two groups to see if there is a difference or a significant difference between them. In contrast, a chi-square test is used to compare observed values to expected values to determine if a difference between observed data and expected data is statistically significant. A classic example of this is if you have an acquaintance. Let's pretend your acquaintance's name is Charlie, all right? So Charlie loves rolling dice. Charlie has been on a winning streak lately, rolling sevens multiple times in a row. Specifically, the die on the left has been rolling a high number of fours, it seems. So people begin to become suspicious. So they run a chi-square test to determine whether or not Charlie's die is loaded. Here's our research question and hypotheses. Now, on a normal die, each number on the die should be rolled pretty equally, meaning you are just as likely to roll a 2 as you are a 5, and so on. So, if a die were to be rolled 12 times, then we would expect to see each number on the die to be rolled twice. These are our expected values. So next, what we do is we then have Charlie roll one die 12 times, and we record the number that Charlie rolled each time in a data table. Let's say on the first roll, Charlie rolls a 2, so we'll mark off 2. Then on the second roll, Charlie rolls a 6, and so on. All right, and we do this until Charlie has completed 12 rolls. So filling in the data table, we get this. From here, we could then run a chi-square test to compare our observed values to our expected values. If we get statistically significant results, meaning our p-value is less than 0.05, that means that the difference between these two data sets are statistically significantly different, meaning that it is very likely that Charlie's die was loaded. So circling back, all right, and this is check-in number 11, mind you. So circling back, based off of the information that you see above, do you think we should use a t-test or a chi-square test to evaluate our data pertaining to bluefish and orangefish fin length? Well, awesome work today. Your final two check-ins, check-in number 12 and check-in number 13 for this topic, are going to walk you through how to run a t-test and a chi-square test on your device. As always, please feel free to reach out if you ever have any questions, okay? And that concludes our Intro to Statistics discussion. So as always, like I said, please feel free to reach out if you have any comments, questions, or concerns pertaining to this topic, because you will be applying your knowledge gained from this to analyze your own data after you carry out your first experiment during our very first in-person lab. Best of luck!